We're moving on now to the covering of forward error correction codes, and in particular convolutional codes, which is covered on Chapter 7. So in the Scholar textbook, we'll be covering these sections, and in particular covering convolutional encoding, how we can do different representations of the encoders, most importantly how the decoding algorithm works, and finally some properties of convolutional codes. So there are two broad categories of forward error correction, one being block codes, the other one being convolutional codes. They both have the same definitions of coding rate, so this idea of k bits uncoded becoming n bits coded. In block coding, each of the blocks which are encoded are isolated and independent from one another. So a block of k bits gets encoded, n bits come out, poof, they're sent, and the next one comes in, and one block to the next doesn't influence one another. There's no memory from one block to another. Completely different in the case of convolutional encoding. So it's true that we take k together to generate n, but instead of throwing away the whole block and going on to another block, we're going to actually just shift that block so that we input some new data, generate a new code word, etc. So it's continuously being encoding the data. And in general, memory of capital K minus 1 blocks of k bits come into it. In other words, when I'm doing my shifting, at a certain point I will have shifted all of the previous bits out that will no longer influence the next one. And what does that take? That's what I call capital K, which is the memory of my encoder, the memory length of my encoder. And we have a special name for this memory length for convolutional codes. We call that a constraint length. So capital K is the constraint length of the coder, and small k, lowercase k, is the number of bits that are being encoded. So this is a general block diagram of a system using convolutional encoders. And one thing I'd like to draw your attention to is this word that keeps coming up. You keep seeing here sequence. And you see that when I'm looking at the data, there's this ellipse, dot, 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 keeps going on. So this is something very different from what we would have seen in a block diagram for a block code. In this case, it's a convolutional encoder. And so we're talking about sequences at the input. We're analyzing, we're getting out sequences of code words. It gets modulated onto some modulation format. It goes through the additive white Gaussian noise channel. It comes and gets demodulated. So now I'm back to coded symbols here. But you can see that the received coded symbols, I'm looking at a continuous stream of them in order to put it into the convolutional decoder. And again, I'm getting a stream of data coming out. So we'll start on the encoder side. So we have an encoder and we have a decoder. I'll start now talking about the encoder, and it's very important that we understand the mathematics and the representation of the encoder so that we can understand the decoder, because it's easier to understand the concept of encoding. It's kind of tricky to understand how the decoding goes, but if we understand the encoder well, we're going to understand the decoder well. So there are many ways that we can examine or implement or visualize or discuss convolutional encoders. And so we're going to be looking at all 6 of these different ways of representing the encoders. So one will be a block diagram of shift registers. One will be a connection of vectors, so to represent the code as a vector. And then we can interpret those as coefficients in a polynomial. We can think of it as a system, a linear system with an impulse response. And we can think of it as a state diagram of structured transitions and states. And that can be represented also in a tree structure or in a trellis structure. So we're going to be looking at all of these. And you may ask, why? Why are we looking at 6 different representations? Part of it is because of the physical implementation. Shift registers is indeed how we implement this in hardware and application-specific integrated circuits. Another one is a manipulation, mathematical manipulation. So I I will show you the mathematical manipulations in terms of polynomials, and we won't go into it more deeply than that. However, when you're trying to determine what is a good code, this representation is very important and becomes involved in very high-level mathematics in order to optimize your codes. And the last part is to understand what's going on as time goes on. So it's sort of the time-dependent behavior of the encoder. And this will be important to understand how we go through the decoding process. So 3 different reasons why we look at 6 different representations of the convolutional encoder. So we'll start first with the block diagram of the shift registers. And we will see that the number of shift registers is determined by the product of the lowercase k and the uppercase k. Remember, lowercase k is the number of bits which gets encoded, manipulated to be encoded, and capital K is the number of blocks of k bits that are involved or have influence on a given code word at the output. So in general, a block of lowercase k symbols will enter this shift register, and out will come n symbols out of the encoder, which will be the code word. The output is a function of the symbol at the input. The interconnections of the shift registers we'll see in this implementation in shift registers determine the actual code function. Now, we're going to examine the case where lowercase k equal 1 because it's a whole lot easier to visualize and to understand. But computers, of course, they have no problem scaling up to a more advanced version of this. And in fact, most codes will use a larger k than 1. But for our purposes of understanding for pedagogy, we're going to be looking at the lowercase k equal 1 case. So this is the block diagram of the shift register. And if I look at this block diagram, I can see the input on this side, output on this side. We can see that each one of these boxes is big enough to have k, lowercase k bits. Now, the number of shift registers I have is related to this capital K, the constraint length, so that determines how many of these boxes I have. How big that box is determined by lowercase k. And finally, we have an output where we have a new number of symbols, and this is determined by the complexity of my code. 2 things determine the complexity, the k and the n also. But n is going to be greater than k for sure. And once I determine what n is, I'm going to have a bunch of operations here that define each one of the elements in the code word at the output. Finally, what I'm going to do is I'm going to take each one of these outputs and I'm going to go one after the other, round robin, and build the sequence of code words which are going to be coming out of this encoder. So this is a little bit of a lot to take in, so let's take an example where I think it'll become much clearer for you. Before we go on to the first example where we show you the shift register, this representation in shift register is also going to be very tightly aligned with how we represent it as a connection vector and as an interpretation in polynomial. So just remember, the interconnections of the shift registers are what determine the code. And then we'll be calling them vectors. We'll be reserving them or representing them in the form of a vector, which will be these connection vectors. And then finally, we'll interpret these connection vectors as coefficients in a polynomial. So that's a little bit of a side, pay attention to what's going on and why we're doing it this way. So here's our example, very, very simple example. Lowercase k is 1, which means that we have this shift register is just big enough to take in 1 bit. The n is equal to 2, so 1 bit gets expanded to 2 bits once it's coded, and therefore we have 1 bit of the code and a second bit of the code. So that's why if we went back, this would have been 2, and now these 2, I'm showing one above, one below, just it's easier to see. And the capital K, which is the constraint length of the code, is the number of shift registers that are in this assembly for the convolutional encoder. So we can see the first code word, so this is U1. How am I going to get the first code word? Well, it's going to be a function of the register. So imagine that this is register 1, register 2, and register 3. So how do I generate the first, in this case, bit of the code word? So I would take the sum, modulo 2, of these binary elements in the shift registers. So if I wrote that as an equation, I would write that as a sum of register 1 plus register 2 plus register 3. In the same way, I would say that the second code bit is also a function, but a different function. Now it's only the first and the third registers which contribute to the second bit of the code word. So I would, shift in, have 3 values in here, make one calculation, get the first bit, make another calculation, get the second bit, and then line them up, first bit followed by second bit, and that is what's being output. So let's think of this as being represented in a vector. So I have this shift register representation, which was our first representation, and our second representation will be in terms of a vector. So the only thing I do is I look at the interconnections, and I see that for the first bit of the code word, all 3 of the registers are contributing. Therefore, I write that in a vector, putting a 1 in each one of the positions. So each one of the registers is used. Now, if I look now at the second bit of the code word that's coming out, there's only the 2. So when I write that as a vector, it's 1, 0, 1, because the first is used, not the second, and the third is used in generating the second code bit. So now that we have this shift register representation, I'm going to start using some vocabulary that will help us in other representations. And that is that I'm going to think of this always as being the first register as being an input buffer. This is how I'm shifting things in. The rest of all of the registers constitutes what's called the state of the registers. So you have the state of the registers, and then I'm going to have the input buffer, which can, in the binary case, take a 0 or a 1. So this is the state, this is the input buffer. So all codes have to be initialized because the registers have to have an initial state. And so the output will always be a function of what this original state was. So we typically assume that the registers are empty, just all zeros to begin with. And if we want to finalize the coding, we also have to end with a bunch of zeros. So I'm going to show you an example, and in this example I'm going to send 3 bits. I'm going to send 1, 0, 1. Now, in order to show you the coding process, I have to have it preceded by zeros, that's the initialization. And in order to just flush out all of the effects of memory, I'm going to have to also be followed by a bunch of zeros. And then I will see the tail end of the effect of encoding these 3 bits. So here is the sequence finally that is going to go into my encoder. I have my preceding 2 bits, the actual message that's being transmitted, and the final zeros at the end. So we start. Time 1. Time 1, what happens? Well, the state of my registers is initially 0. These are these first 2 that I shifted in. I shifted in those 2 because that was my initial state, and then the first bit is in the input buffer is 1. So you can see that at time 1, I have taken these first 3 and shifted them in. Now I do the calculation. I say 1 plus 0 plus 0, that gives me a 1. Sure enough, U1 is 1. And 1 plus 0 plus 0, that gives me 1, and the second bit is also 1. So I shift in again, and now I can write that I'm shifting to the right. So what was 1, 0 here becomes the 1, 0 here. So now the state is 1, 0 for this encoder, and the input buffer takes in the next bit right here, puts in that 0. Now I calculate again what is the output of my encoder. So I say 0, 1, 0, add them all together, I get a 1 for U1. Now I have 0 plus 0, and I get a 0 for U2. Next time instant, I shift right again. So this 0 gets out, it's no longer there. I have 0, 1, that becomes the new state, 0, 1. I input my new bit into the buffer, which is a 1. Once again, I do the calculation, and this time 1 plus 1 equals 0 for the first bit, and 1 plus 1 equals 0 for the second bit as well. Now, that's the end of the input of the data, 1, 0, 1, but I have to flush it out with my last zeros to get a final definitive transmission. So here, again, I shift over. This 1 gets shifted out entirely. This 1, 0 now appears as the state of the encoder. And the new, whoops, here we go. The new bit that I send in, this 0, is now in the input buffer. Again, I calculate. 0, 1, 0 gives me a 1, and 0 plus 0 gives me a 0 for the second bit. So I keep doing this, keep shifting to the right, and I keep doing this until I have completely flushed everything out, and there's only zeros left at the end. So what do? I start picking out, what were the outputs, and I line them up, and here I see the output sequence. And this is my encoded sequence.